chapter, and the name of the chapter is plate girder design. So first of all, we have to understand that what are the plate girders and how they are different from conventional hot rolled beam section, and in what case we need to design the plate girder, what are the design considerations and the specification that we need to follow to design the plate girder. Okay, first of all, let me give you the overview of the plate girder. Then I will maybe read out these slides. Maybe I don't need to read out these slides if I'm going to explain what are the plate girders. So actually the plate girder, they are also beam, but they are special type of the beam. So what is the definition of the beam? For example, beam is a line element which is subjected to transversal loading. So any line element which is subjected to transversal loading, so it will be subjected to internal forces, shear force and bending moment. And the major deformation will be the deflection. So depending upon the shear force and bending moment and unbraced length of that beam, we can select any suitable section for that beam. That section may be any hot rolled section, hot rolled W section, it could be hot rolled built up section and channel section. But sometimes the we cannot use a conventional hot rolled section for a beam. There are many cases. So maybe a couple of the cases I can explain. Number one, when the load is very heavy. If the load is very heavy, so maybe to satisfy the applied bending moment, we may not have a very heavy section available in the market. So because hot air section, they are made as per ASTM standard. So their dimensions, they are fixed. So it means that if the heavy beam section is not available hot rolled, so in that case, we need to make our beam section ourselves. We need to fabricate ourselves. So you just can say that there are two type of the garments available. One are the ready-made and other are the tailor-made or custom-made. So in the same way, our plate girder beam is a tailor-made or custom-made beam that we can fabricate with the help of three separate plates. Two plates, they will serve as a blank plate and one plate will be used as a web. And then we need to connect these three plates by any mean of connection, maybe by welded connection or by fastener type of connection. So I think one student, he has joined in the lobby, maybe no, he's still not here. So in that case, what we need to do, we need to go for the uh, plate girder design. And other reason is that sometimes we need to achieve a longer span. So if our beam span is very long, so in that case, if the span is very long, then you know that deflection is the function of the length of the beam. If you see all the deflection formula, so almost deflection is the cubic function of the length in case of the point load, and maybe the length power 4 function in case of UDL load. So if the length is very large, then this beam will have a larger deflection. So if we want to control the deflection, so we need to increase the moment of inertia of the beam. So by increasing the moment of inertia, we need a very deep beam or a beam which is having very large depth. So if we are using a beam with very large depth, it may be uneconomical or that might not be available in the market. So in that case, we have to make beam by ourselves, and that type of the beam will be referred as a built-up beam or built-up beam section, which is called as a plate girder. Why it is referred as a plate girder? Because we are using three separate plates to make that beam girder. So a plate girder is a beam built up from separate plate element welded or riveted together. Our simplest maybe plate girder is comprised of two flange plates and one plate which will be used as a web. And they are connected by the welded connection, and sometimes we may provide the stiffening plates along the web or sometimes we may not provide the stiffening plate. So what are the stiffening plate? I will show you the in upcoming slide and I will move back. So here I have told you that sometime what we do, but in plate girder always, to increase the shear capacity of the web, we also provide a plates between the flanges, or we connect the web by a vertical plates, or these plates are referred as a stiffening plate or stiffener. So we provide the stiffener at suitable spacing along the length. What is the function of these stiffening plates? They increase the shear capacity of the web. How it increases, we will study in detail in our plate girder chapter. So sometimes we may only use three plates, two as a flange and one as a web without stiffening plate. And sometimes we need to provide these stiffeners or stiffening plates to increase the shear capacity. And what is the design criteria? So obviously we will cover in this particular chapter. And um, so in a typical beam, if you visualize, I believe that you are already familiar with the bending stress and the shear stress. Bending stress or the flexure stress, if you know, they are maximum at extreme fiber and they are zero along the neutral axis. So are maximum. So maybe in case of the eye girder, we can say that bending moment or the bending stresses, they will be maximum in the flange. And on the web, they will be almost negligible or they will be very less. So what I can say that normally in eye section girder, because in eye section girder, area of the flange at extreme fiber is more than the area of the web. So almost maybe 90% movement is resisted or taken by the flanges, and 10% movement might be taken by the web. But we are assuming that all the movement is taken by or resisted by the flange, and web is not providing any resistance toward the movement. So it means that when we are designing the flanges, so the movements, the flanges, they will be designed to carry the movement. So it means that assuming web is not contributing, so the flange side may be a little bit on the upper side because that some movement which is taken by the web is also considered to be taken by flanges. And similarly, if you visualize the distribution of the shear stresses, so shear stresses is parabolic and the shear stresses, they are maximum in web and they are zero at extreme fiber or flanges. So it means that we will assume that all the shear force or the shear stresses, they are resisted by the web. So it mean that in plate girder, we will determine the flange size based upon bending moment, and we will determine the size of the web based upon shear force diagram. Okay, one more thing. In hot roll section, normally maybe I will show you the my previous lecture, then you will have a better idea that what I'm going to explain. For example, when we solve this example, so in this example, uh, let's suppose we design our beam section based upon this bending moment. Actually, we design the hot roll section based upon maximum bending moment diagram. And then we have to accept that section and just we verify the shear capacity. For example, applied bending moment is 540 and maximum shear force at any point of this beam is 118. When we selected the beam section based upon this moment 540, so we have selected this section. Which one? W, not this one. Okay, maybe this section W690 into 125. And this section is selected based upon maximum bending moment. So when we selected this section, So the moment carrying capacity of that section was 665, which is more than our applied bending moment. So bending check is okay. But when we check the shear capacity of the same beam section, so shear capacity is coming out to be 1070.9. So, but our applied shear is 118. It means that shear capacity is almost maybe 9 times more than, or maybe you can consider 8 times, or 10 times more than applied shear. It means that web is too strong as compared with the maximum applied shear. But we can, it means that we are having excess of web area in excess. We can reduce the web element or web thickness because we can optimize, but we cannot do because this is the hot roll section which is selected based on bending moment. If you want to select a section which is having shear capacity maybe 150, just more than this, 118, but that section will be satisfying the bending moment criteria. It means that in this case, we cannot optimize this. We have to select or use the same section. But in case of the plate girder, we can design the web as per our requirement. We can use a thinner web. So by using a thinner web, we can reduce the weight of the plate girder and also we can achieve the economy because we are cutting the metal. Okay, one example I will give you. For example, we are having a plate girder whose depth is 1 meter and the length is maybe 10 meters. And instead of using thickness of the web as a 10 millimeter, if I'm using 6 millimeter, it means that I have saved 4 millimeter thickness. 4 millimeter multiplied by the length of the plate girder and multiplied by the depth. So this much volume the plate girder we have reduced. If this volume is multiplied with the density of steel, so we have saved too much material. So structure will also be economical and the weight of structure will also be less. If the weight of structure is less, then the end reaction on our column will also be less. So it means that column will they will also be the economical. So some difference. So when we studied the definition of the compact section in case of the beam, so I gave you the four conditions, and these four conditions I will give you the overview again. So we studied the four area for the compact section. Flange must be continuously connected with. There must not be web local buckling, and there must not be any flange buckling, and unbraced length should be than LP. So there were four conditions to classify the beam section. So beam section may be compact, non-compact, and cylinder. So flange local buckling, we are having two values, lambda p and lambda r value. So in case of the hot rod beam section, web is continuously connected with the flange. Lambda f value is less than lambda p. We are having two limiting values, just like we are having LP, LR. Similarly, we are having two limiting values for the flange, lambda p and lambda PR. Similarly, for web local buckling, we are having lambda PW and lambda PR. Oh, sorry, lambda WR. So in case of the hot rod section, flange is always compact, web is also compact, mean that lambda F and lambda W is less than the corresponding lambda P value. It means that the class of the beam section may only change due to the later torsion buckling criteria or unbraced length. If unbraced length is less than LB, our section will be the compact. If unbraced length is more than LB but less than LR, our section will be non-compact. If unbraced length is more than LR, then our section will be cylinder. But now, in case of the plate girder, our section beam or plate girder may be compact or non-compact based upon flange local buckling and web local buckling. So these are some difference from the hot rolled section. So what I can say that in case of the plate girder, our flange plates may be compact or non-compact, but that may never be the cylinder. So if you want to uh, maybe brief me, for example, if I want to simplify, so I can write that maybe if I am having the lambda value over here. So lambda of the beam section or flange lambda will always be less than their corresponding lambda r value. Okay, anyhow, I will explain you when we are computing the formula. So flange, they may be compact or compact. It means that our plate girder may be compact or non-compact based upon flange local buckling criteria. Hot roll beam section is always having the compact flange. Similarly, in case of the web, so in case of plate girder, our web will always be cylinder. It means that always be cylinder mean that for web, in case of the hot roll section, lambda W is less than lambda P of the web, which is maybe this 3.676 E over Fy. So this value is lambda P. Similarly, we are having lambda R value for the web also, which is having a different that I will show you in LRFD reference say when we will, yes, this one. Different web with purely in flight. This is the lambda R value for the web. Lambda R is 162, which is computed by this, and lambda P value it is computed by this formula. So in case of our hot roll beam section, so lambda W is always more than this value, 5.7 and of under root E over Fy. So I can say that in case of the plate girder, our web will always be cylinder. It will be, it means that it is very thin. What implies that web will always undergo elastic buckling. So the depth over thickness ratio of the web is always greater than 161.2. So I can say that lambda W is more than lambda R value. So our web will always be cylinder. So based upon web local buckling, our web will always be more than 161.2 for A3060. And actual expression is 5.7 100 E over Fy. So this is, you can write 161.2 approximate. I have written the approximate value over here. So what does it mean? It implies that our plate girder section will never be a compact section. our plate girder is always non-compact. Why? Because first condition is not satisfied, because flange may not be connected thoroughly with the web if we are using the fastener type of the connection. But if we are welding the web plate with the flange plate thoroughly or throughout the length, then based upon first criteria, our plate girder may be compact. Then flange plate, they may be compact or non-compact. So our section being a plate girder may be non-compact based upon flange local buckling. Similarly, based upon web local buckling, our plate girder will always be cylinder. Why it will be cylinder? Because we are keeping the lambda W value more than 161. But this value will always be less than 320 because we do not want to reduce a very thin web. So we are having the lambda W. What is lambda W? Height of the web over thickness of the web ratio between 161.2 to 320. So where we are getting this 320 value, I will explain in upcoming slides. Arrangement of plates in which the flanges are designed for movement and web is designed for shear uh, help to achieve efficient cross section than is possible with hot rod section. Efficient means that we will have economical section. It means that we will just have the flange dimension as per our requirement and web dimension as per our requirement based upon the shear force. The other most important component of the plate girder is stiffeners, which is used to provide indirect stability to non-compact web. Yes, that is very important. So here, if I say that our web is cylinder based on web local buckling. So again, let me give you the definition of compact section again. A compact section is the one which can achieve its full plastic movement carrying capacity. And non-compact section is the one, or non-compact web is the one which will partially fail due to the yielding stress and partially fail due to the elastic stresses. And elastic web or elastic section is one which buckle or which become unstable at a stress value much less than yield stress. It means that if web is cylinder, it will not fail due to yielding. It will buckle, and it will buckle at a stress value maybe much lesser than the yield stress. It means that we are unable to achieve full capacity. Then how we can enhance the capacity of the web? Then we can increase the shear capacity of the web by providing the stiffening plate or stiffener. So plate girders are economical where the spans are longer and up to permit the uh, cost by proportioning the particular requirement. So they are economical for longer span or for very heavy load. So labor cost for assembly such as plate girder is generally higher than that by using hot rolled section, which may offset the saving in materials. So labor cost is little bit more in case of the plate girder as compared to the hot rolled section, because we need to weld the two plates. We need to cut the plates and then we need to weld or maybe connect by the fastener. So extra labor cost is involved. It means that the material that we are saving by optimizing the section may be compensated with the labor cost. But anyhow, what advantage we are having? We can reduce the overall weight of the structure. If the weight of structure is reduced, it means that a lesser load is transferred to the column and the foundation underneath. So we may have two type of the plate girder. So first one is the riveted or bolted fastener type of the connection. So this is the a line diagram, but I will show you some actual picture. So here you can see that we have used a one plate as a web and used as a flange, maybe in combination. Why they are using three plates? Maybe uh, the total flange width may require is 30 millimeters. And in a market, we do not have 30 millimeter thick plate. Instead, we are having a 10 mm thick plate. So we can use the combination of three plates to achieve the total depth. So three plan plates, they are connected with the web with the help of angle section, because an angle section, an extra section is used to connect the flange plates with the web. So one side of the angle is fastened with the flange plate, and other leg is used to fasten or to connect the web with the angle. So extra angle or an auxiliary angle section is used. And here you can see that three plates at this section, but at the end we are having only two plates. Why we are having two plates, I will explain later. So then this is the angle section that is used throughout the length. Here you can see this is protected. And then we are having this stiffener, two type of stiffener. One is intermediate. This is also used as a angle section. So this is the projected leg, and the other leg, flat leg, which is used to connect the angle with the rivet or fastener with the web. So this is a stiffener, which may be the combination of two angles or combination of multiple plates, and this is referred as a bearing stiffener. So these stiffeners are used above the force reaction or under any concentrated force to avoid the crushing or crippling of the section due to the concentrated force. Okay, here this is the typical plate girder, bolted plate girder, sorry, riveted. So this picture I have taken at River Ravi. So here you can see that this is a typical plate girder. A bottom section is an angle section. If we require the thickness of the flange very less, so the flange plates, they may be served as a sorry, the angle, they may be served as flange plates. So there, this projected leg, it can be used as a flange. So you can see that, and here you can see an extra plate is also welded to increase the thickness of the flange. Why it is welded, I will explain in next slide. Okay, here you see that this angle section is riveted with the web, and here you can see these stiffeners are also comprised of angle section, and one leg is connected with the web and other is projected, and stiffeners are provided between the inner side of the flanges. Okay, here at this port, you can see that in steel structure we can actually provide a hinge. So this is a hinge. So this point, it cannot translate in horizontal and vertical direction, but due to the flexion, it can rotate. So this is a typical hinge sport, and here you can see that they have used one, two, three, and four angle sections as a bearing stiffener. So this complete portion is referred as a bearing. Why? Because a sports section is very heavy or concentrated. So to avoid the crushing or the crippling or the stress concentration, so we use the plates in combination, or we need some larger plates or a thicker plates to resist the end reaction here. So again, in case of the welded connection, the configuration is rather more simple. We are having one plate, two plates as a flange, and one plate as a web, and we are using these welded connections to connect the uh, flange with the web, and weld it is welded maybe intermittently or throughout the length. And then to increase the shear strength of the web, stiffening plates or stiffeners are provided. These are also flat plates between the flanges. So here you can see these are the intermediate stiffeners which are provided at certain spacing. And spacing of this stiffener is referred as a A. And above this force, the two plates, they, so thickness of the flange is referred as a TF, thickness of the web is referred as a TW, width of the flange is referred as a BF, and height of the web or the depth of the web is referred as a H value, which is the distance between the inner faces of flange. So here, this it is a typical welded plate builder. So I got this picture from one of my friends who actually designed this project while working in Izhar group of companies. And this builder, they belong to Assembly Hall in Beacon House School, which is constructed in DHA Phase 5, maybe in 2012 it was constructed. So here, why they are using the plate builder? Because in Assembly Hall, they need a larger span without any support. So they want to attain the longest span without any anterior column. So in that case, they have to opt this option, plate builder. So here you can see that the shear connector, they are stirrups. So when the concrete will be poured, so unbraced length will be almost zero because they are not using typical stud, but a stirrup type of the shear connector. When the concrete will be poured, so this stirrup will be embedded with the concrete, so they will not let the top line to twist in later direction. And here you can see that the stiffening plates, they are also provided. And one interesting thing is that you can see depth of the girder is not constant. You can see depth is more in the center, but it is less at the end. So it means that it can also be optimized depth based upon the bending moment. So why the depth is less? Normally, our design equation is applied bending moment is equated with the moment carrying capacity. So we are having two formula, either the section modulus multiplied by yield strength, or we know that due to the bending, the flexure stresses are produced in the flange area. So if these flexure stresses, they are multiplied with the area of this flange, so that can be converted into compressive. So top line is subjected to compressive force and bottom section is subjected to tensile force. This means that if we are assuming all the stresses, bending stresses, they are resisted by a flange, then we can assume this compressive force is acting in the center of the flange, and movement produced by this compressive force about neutral axis will be equal to C into lever arm. So this compressive force multiplied by lever arm is equal to the movement produced by this compressive force, which is equal to movement carrying capacity of the plate builder. So we can consider phi b mn movement carrying capacity as a phi b compressive force into lever arm. This compressive force in the flange we can convert into stress multiplied by the area of the flange plate, because we know that stress is equal to force over area. So force will be equal to stress produced in the material into the area. So lever arm we can consider as a d by 2 or h by 2. So h by, we can assume that thickness of the flange is 0 almost. So d by 2 may be equal taken as a half of the depth of the web. So this flange will fail due to yielding when applied stress will be equal to yield stress. So we are assuming that the stress, failure stress in the flange plate are equal to yield stress. And then area of this flange plate may be equal to width of the plate into thickness of the plate. So we can refer as a FYBF into TF. And lever arm is equal to D by 2. Okay, now if we substitute this phi b mn value over here, so we can equate applied bending moment with this equation. Okay, in hot rolled beam section, actually we are only selecting the beam section based upon maximum bending moment. For example, M, which is acting at the center. So this maximum bending moment is just produced at a small portion. For example, at this portion, maybe point, applied bending moment is not M, rather M1. It means that if at this point, if the moment is less, then at this point we may require a lesser beam section, because if applied bending moment is less, so we can optimize it. So how we can optimize? There are three techniques. So let's suppose if mu is equal to m, so we will have maximum value of the bf, tf, and d. If we have determined the d, tf, and b value, so if at this point movement is less, m1, if we replacing the mu value equal to m1, so it means that just to balance this, we also need to reduce some parameter in this equation. So we can play with the depth, either thickness of the flange or width of the flange. So let's suppose what we do, if we keep the depth of the plate girder constant throughout the length, width of the flange constant, then we can reduce this mu to m1 moment by reducing the thickness of the flange. So it means that we require a less thickness in the middle, and at this section we can reduce the thickness. So that's why here we have used the three plates, and at this point we have used two plates. And similarly, at this point where the moment is m2, we can further reduce the thickness of the flange. So a better example you have already seen here. So why the three plates are used? Because at the center movement is more, so we need larger thickness. So at the end, movement is less, so we need a lesser thickness. So that's why two plates are provided. So another way is that if we don't want to reduce the thickness of the flange, we can reduce the width of the flange by keeping the D constant. So maybe at this point we have the larger flange width. At this point we will have lesser flange width. Other thing is that if we do not want to change the flange dimension BF and TF, so we can reduce the moment by reducing the depth. And this process is used over here, because at the end movement is less, so that's why depth is reduced. And in the center movement is more, so larger depth is used. But we have to use some minimum depth here. It doesn't mean that movement at the end is zero, so depth will be zero. So we need some web depth at the end, because at the end we are having shear force. So we need some minimum depth of the web at the end to satisfy the applied shear. So it means that we can also optimize the plate girder based upon the shear force and bending moment diagram along the length. And similarly, we can compute the depth of the web by using this equation. We can equate the applied shear with the shear capacity, and we can assume that I have used VU, but so we'll see this formula. So actually, the web dimensions are mainly based on many criteria, but I will give you the one idea. If we know the applied shear, we know the yield strength, so we can assume compute the area of the web by using this equation. So we just compute the area of the web as per our requirement. So I will, this is the last slide that I will cover today. So plate gutters are economical for railroad bridges which are subjected to heavy load. For example, on our canal road, you can see that on canal, you can find lot of the railway bridges. So even though the span is less, maybe the canal may not be having the width more than maybe 10 meters, maybe 30 feet. But due to the very heavy load, we need to design the plate girder. And for highway bridges, if the span is more than 24 meters, then we also go for the plate girder for the economic consideration. So they are often very competitive for longer span, particularly if the span they are continuous. Because if we are having continuous span, so bending moment is reduced. Because in a continuous beam, uh, maximum bending moment is mega L square by 24. Oh, sorry, mega L square by 12. So in case of the simply supported case, so the moment will be mega L square by 8. So even though if the load is very heavy or the span is very large, so we need to go for the truss bridges, because in case of the truss we can achieve the larger depth, and by using this skeletal member we can save lot of material. So plate girder are also used for the building structure if the span is larger. So a typical example I have shown it here. So next time when we will start, so I will start from this uh, slide number 11. So if anyone is having any question, so he can ask me. Any student? Okay, the student who are present, please raise your hands. Just 10 minutes ago, there were 35 students present, but now 41. But anyhow, I'm having the log file. So 56, are you not there? Roll number 56. Okay, there. Who is Ayan
There
20? Okay, okay.
present.
Ayan 29. Mr. Ayan. And Fida Bhatt, Mr. Fida Bhatt. ओके सीआर इसका रोल नंबर नोट करो, ये फिदा भट्ट का।
ओके सर।
ये प्रेजेंट नहीं है। ओके सीआर, मेरे पास यार वो तमाम कैंडिडेट्स मैंने डाउनलोड की हुई हैं, तो इनकी क्लास की एक एक्सेल की लिस्ट भी बनाई हुई है। एक्चुअली मुझे इनके रोल नंबर और नाम का नहीं आइडिया, बिकॉज दे आर यूजिंग देयर पर्सनल ईमेल्स, तो वो मैं आपको सेंड करूंगा।
सर वो जो एक्सेल शीट आपको सेंड की थी उसमें ईमेल के साथ नाम और रोल नंबर भी था आई थिंक।
अच्छा, वो मैं आपको बुला क्या करूँगा, अब मैं वो आपको सारी अटेंडेंस से आपको भेजूंगा और आपने वो मुझे मार्क करके देनी है।
ओके सर, ठीक
है, वो मैं आपको व्हाट्सएप कर दूंगा, मैंने सारी डाउनलोड की हुई हैं और एक्सेल की शीट भी आपको भेज दूंगा। ठीक है,
ओके सर,
ओके, गुड लक। अच्छा यार, मुझे ये बताना है, अभी आपने ना मुझे अभी शाम तक बता दो कि अभी मैंने आपसे कंप्रेशन मेंबर तक के तमाम लेक्चर के लिंक शेयर कर दिए हैं, ठीक है ना, और बीम के नहीं भी किए, तो बीम के भी हो जाएंगे। मिड टर्म में ना आपका वो मैं अभी डॉक्टर कासिम से मिलके पूछ लूँगा कि वो कहाँ तक कोर्स डिसाइड करना है, तो इंशाल्लाह इस वीकेंड पे आपको बीम वाले भी सारे लेक्चर के ना वो लिंक मिल जाएंगे, वो डाउनलोड हो गए हुए मेरे पास। तो आप मुझे बता देना कि कहाँ तक लेक्चर नहीं है, जिसका लिंक अवेलेबल नहीं है या नहीं चल रहा वो भी मुझे बता देना शाम तक। ठीक है,
ओके सर,
ओके, सी यू इन द नेक्स्ट टाइम।